We talked about all these different ways of naming things, and hopefully you got a chance to practice that in your homework, since I guess everyone thought we had a quiz today. So now you get a couple more days to practice it if you need to. But moving on now, we're going to look at some of the reactions. So far we've just looked at, here's the structure, here's how you draw it, here's how you name it. Now let's talk about what these things actually do. And we'll talk about a couple reactions of the double bonds. Remember, we said that compounds like this don't really react outside of combustion reactions. I mean, there's other stuff that they do, but primarily we use them as fuels and we burn them. Whereas something like this, a double bond, can have a much broader way of reacting, or much broader possibilities for reactions. So let's look at some of those. The kinds of reactions that we're going to look at first are called addition reactions. And these are just one molecule adding with an alkene, so them coming together. When we draw these types of reactions, we don't just write a chemical equation like we do for the inorganic compounds, because we want to know not just this molecule's formula and this molecule's formula, but we want to know where they connect and how they connect to each other. So we use the structures instead. So we might draw a basic alkene like this, and just some basic thing with whatever connected to it where we won't specify it. And then we react this with hydrogen, which is H2. We can draw it out. And then in an organic reaction, we've seen this in some other reactions too, but the two main molecules that react are written, this plus this, and then over the arrow or under the arrow is whatever other stuff is involved in the reaction, maybe the solvent or some other parts of it. In this case, it's going to be the catalyst. So that's platinum, palladium, or nickel. Not all of them together, but one of those can be used in this reaction. And what you do is you take your molecule. Remember, hydrogen's a gas. So you have to put this thing in some sort of a chamber that you can pressurize with hydrogen gas and in the presence of this catalyst, this platinum, palladium, or nickel catalyst. Just literally some of the metal, usually in a really fine powdered form or something like that. And what that does is it allows this catalyst allows the alkene to react with the hydrogen, and one hydrogen atom goes to each carbon of the alkene. So what you've in effect done here is you've saturated the alkene. You've turned the alkene into an alkane. And this is known as hydrogenation. So you combine the alkene with hydrogen, the hydrogens go to those carbons, and now it's not an alkene anymore. Now it's an alkane. You can do this in much larger molecules as well. So let's see what this looks like in a line structure. Let's say we took this molecule. What would you name this one? Practice a little bit. Close. It's got 6, so the hex part was right. But what else is there? Cyclohexene, right. So this would be cyclohexene. And if cyclohexene is hydrogenated in the presence of a nickel catalyst. One hydrogen goes here, one hydrogen goes there. So we could draw that out like this. But remember, in the line structures, we don't usually draw the hydrogens, right? So what we would really draw as a product is just the cyclohexane. So we've turned cyclohexene into cyclohexane. Yeah, but remember, we're not removing the double bond, we're adding hydrogen. And yes, the effect of that is that there's no longer a double bond there. So the electrons that were used in the double bond, if you imagine these two electrons here, are now involved in these covalent bonds with the hydrogens, so they can't bind with each other, because carbon can only have 4 bonds. This is an important process in fats and oils. Did we talk about that? I didn't. No, not yet. So does anybody know what a fatty acid looks like? In terms of, does anybody know what a fat looks like? What do you think? How would you? I mean, at the molecular level, a molecule of a fat. Kind of full of stuff. It's kind of like this. So you have this molecule. We need a little more space here. Start over here. This molecule is glycerol or glycerin, which we've done before with a hydrogen there. And so what you do is you combine this with 3 molecules called fatty acids. And fatty acids are these long, long carbon chains, like maybe 16, 18, 20 carbons or more. So you put 3 of them on there with this glycerol, and that's known as a triglyceride, which is a fat. Okay. So that's what it looks like. It's this big kind of molecule, and actually this middle one ends up flipping out the other way, so it looks kind of like a fork kind of a configuration. But these individual fatty acids can come in various different structures, and they can either be straight chains with no double bonds, which are known as saturated fatty acids, or they can have double bonds, which are known as unsaturated fatty acids. So the unsaturated ones might look something like this. Unsaturated fatty acids all have cis double bonds. So they get these kinks in the chain. They end up not laying nice and flat. And that's why saturated fats tend to be solids and unsaturated fats tend to be liquids. So saturated fats are things like butter, animal fat, human fat, solids. And unsaturated fats are things like olive oil, other vegetable oils, which are liquids. So we talked a little bit about trans fats and that kind of stuff last time, right? So this is that process. This is that hydrogenation process where hydrogen is added to these unsaturated fats, making them saturated. Now, if that reaction is done fully, all you've done is turned an unsaturated fat into a saturated fat fully, and that's what happens. That's what shortening is, for instance. Shortening is unsaturated vegetable fat that's been fully hydrogenated to become saturated fat, to become a solid. The problem we talked about last time is when you have partial hydrogenation, that's when you're left with the trans fats, where they still have the double bond, but they have a straight chain like a saturated fat, and that can cause a lot of problems. So that's what the reaction looks like. The next one we're going to look at, and then we'll practice writing products of some of these. The second type of addition reaction is known as hydration. So what do you think hydration is the addition of? Water. Just like when we hydrate ourselves, we drink water. So we have, again, an alkene And we're going to add water, but I'm going to draw the water a little bit weird. I'm going to draw it as HOH. And this one doesn't use a metal catalyst, but it uses an acid catalyst. Right? H+, so that's an acid. Could be HCl, H2SO4, whatever. There's various acids that are used for this. Sulfuric acid is a common one because it doesn't have other side reactions. So if that's done, the hydrogen goes to one carbon and the OH goes to the other carbon, just like the HH. Same thing we just did, but now it's with H and OH. So now this product is going to be like this. And that's called hydration. This is what's known as a functional group. Something that is not carbon or hydrogen that is connected to an organic compound. And OH is known as an alcohol. I don't think we'll get into a lot more of these in the chapter 12, so we'll stick with that one. I think if you look at the old exam, the old third exam, there was a question about functional groups. So I don't think we're going to get there on this one. All right, so that's hydration. So let's look at that again in a different type of structure drawing. If we take cyclohexene again, and we react it with water, with an acid catalyst, does it matter which side we put the H or the OH on here? No. It doesn't. Why not? Yeah, it's all symmetric. So if we put it on one side or the other, it's the same molecule. And remember, we don't show the hydrogen, so really it added a hydrogen here on this carbon. But we don't need to show that explicitly. So we have this. So this is known as cyclohexene. This is known as cyclohexanol because we've now made this alcohol. We won't go into the rules of naming other stuff like alcohols, but that's what that would be. All right. So one thing that happens here is sometimes, let's take a molecule like propene. Here, but because we're using a line structure, we don't show it. So here, if we count on the carbon, this carbon has 1, 2, 3 bonds showing, which means it needs one more from a hydrogen. Here we have 1, 2, so that means it has 2 hydrogens. If we draw that out explicitly, that had 1 on that, now it has 2. And this carbon had 1, and now it has the 1 and the OH. See that? So here are the things that were added. One of the hydrogens from the water went here, and then the OH from the water went over here. So sometimes you have an asymmetric double bond like this, where it does matter which one goes on which side. So if you imagine the same procedure here, there are 2 possibilities. We could put the H here and the OH on the end, or we could put the OH in the middle and the H on the other side. And in this case, this does not form, this one forms. So how do we know? There's a rule that we can look at. If you go on to take organic chemistry, you'll learn where that rule comes from and why it works that way. But the key is to focus on where the hydrogen goes. The hydrogen can either go on the CH or the CH2. And the rule is that the hydrogen goes to the carbon with more hydrogens. So look at that again. The hydrogen could go either to this carbon that has one hydrogen or this carbon that has two. So it picks the one with two. And then the OH goes to the other spot. So when you do have that asymmetry, you have to keep that in mind. Let's look at another example of that. In a line structure, that can be a little bit tougher because we don't see all the hydrogens explicitly. But there's nothing wrong with just writing them out on your own when you encounter that so that you can see them. So in this case, which is the correct product? This one or this one? Based on that rule above. What do you think? What? Let's think about this. So let's draw out these hydrogens. There's none over here. There's one here, right? So that means this first one, the H from the hydrogen went on where the other one already was. And the second one, the hydrogen from the water went up here. So which one shows this black H going to the one where there's more H's? Yes, which very funny. The first one. So there was already a hydrogen here, so that's where this hydrogen goes. So this is that's the product. That's the preferred product in the addition reaction. All right. I'm lost here. Sorry, my thing quit on me a second. Okay. So we're going to talk about one more thing that's related to double bonds. This is what we call aromatic compounds. Does anybody know what that refers to? It sounds like something to do with smelling. Yeah, but actually that's not right in this case. It's an old name because, yes, some of the first things that were discovered that work this way were indeed smelly. But now it refers to this class of materials that's made up of rings, so cyclic structures, with alternating double bonds. So the classic example of this, or the most popular, most common one, is this one. Oops, these are kind of funky. A 6-membered ring with alternating double bonds, which in a line structure looks like this. And this is known as benzene. So benzene is a really common structure. By itself, it's a carcinogen. So we don't use like just pure benzene much. We used to, but not so much anymore. But as a part of larger molecules, it's everywhere. It's an important part of a lot of molecules in your body. It's in amino acids. It's in all kinds of other stuff. So the reason for that is that these types of molecules have a special stability. They are far more stable than other molecules. And because of that, they form quite readily and do various things. So some common, or one thing that we're going to do is we're going to use benzene in naming. And it's actually pretty simple. It's the same types of naming rules that we've already gone through. So what do you think a structure like this might be named? Well, actually, you don't need the cyclo. Just benzene is that. It's just benzene. But what do the CLs tell you? How do you deal with those? Yeah. Keep going. Right. Well, we've got benzene is going to be the main part. And then we have 2 chlorines coming out. So that's going to be dichloro. And then how do we number them? Yeah, 1, 2, because they're right next to each other. So we can start either place and go 1, 2, numbering around the ring. So this becomes 1, 2, dichlorobenzene. There are some other common benzene derivatives that you don't need to memorize the names of, but we'll just talk about them because they'll come up. If there is a methyl group on benzene, we don't actually call this methylbenzene, although that would be the proper systematic name. But rather than methylbenzene, we call this toluene. Toluene is a really common solvent, meaning you can buy it at the hardware store, dissolve stuff in it. A lot of glue, like I think rubber cement or model glue, is based on toluene, so it has a pretty particular recognizable smell. And if you take toluene and you put some of these NO2 groups on it, you have 2, 4, 6 trinitro toluene. Anybody know what that is? That's abbreviated TNT. That's dynamite. Blow stuff up. We actually had a nitro benzene type compound in here last year that we didn't know about. It was kind of hid in the back of a room. And if this stuff, this particular compound, which is related to this, if it dries out, it becomes shock sensitive, which means if you hit it too hard, it just explodes. So we found out we had it, called in a special hazardous materials team that came in with like suits and everything, and they got it out of there. But it actually did explode once the bomb squad guys got in there.
Bomb squad?
Well, it's like a hazardous materials, but who deal with that. So they had the suits. They tried to open the bottle to put some water in. That's their job, to put the water in. Because if you can get water in it, it's not dangerous anymore.
Oh.
So they were trying to open it up to get some water in it, and then they could just take it out normally. But when they unscrewed the cap, some of it was stuck under the cap, and it went. So it wasn't a big deal. Yeah.
Was it a big drum?
No. I mean, I don't know. I was here.
Class dismissed?
I was here. It was a Friday. Nobody was here. I didn't hear anything, and they had all the like control blast shields and everything all around, set up around it. So they were expecting it to do that, but it was kind of exciting. Yeah.
Like a white suit?
I didn't see him
Like
put it
you see in
on.
Grey's Anatomy?
I don't know.
That's serious stuff.
Yeah.
That could have been really bad.
Right. Yep.
When that happens, do you like pass everyone with like, pass or fail for the class?
What?
Like if something like you say that were to happen, like an explosion
Yeah.
of a bomb,
Right.
do you still like pass the students? Just like,
I don't think so.
um,
I would imagine if it were something that like the building exploded or something, you'd probably get your money back. Yeah. I don't know. I don't make those decisions. So anyway, these are these aromatic compounds. So you want to look for these kinds of things. And they pop up all over the place. You can have multiple ones connected to each other if they're sharing a couple carbons like this. This is known as naphthalene, which is mothballs. I don't know if anybody uses mothballs
why do you
anymore,
keep
but
them in your closet?
what?
Why do you keep them in your closet?
Because they repel moths. So moths don't come in and eat all your clothes.
Oh.
Like wool especially. So they're using like camping equipment because older, I don't know if it's as important anymore, but older things like canvas and wool that aren't really used for technical stuff anymore. Before we had synthetic materials, moth larvae would come and eat holes. Like if you store your sweaters in a box or something, that you get them out and there's holes all over them.
Like a particular stench to it.
Yeah. Yeah. So a lot of more people prefer to use like cedar, which is a nicer smell and does the same kind of thing. And then you can connect them a different way. You can just have them, the two rings connected but not sharing any carbons. This is called biphenyl. And if you put a bunch of chlorines all around this, you have what's called polychlorinated biphenyl, which is abbreviated PCBs. Anybody know what those are? That's printed circuit board, same initials, but yeah. PCBs are a toxic compound that have been released into a lot of water sources in the country. So a lot of places, like if you can't eat the fish from a particular lake or a river, a lot of times it's because of these high PCB levels because they accumulate in the environment from being dumped from hazardous waste from companies over the years. So a big part of this is, yeah, these are everywhere and they are in your body and you need them and vitamins have them and all that. However, we also know that a lot of these types of things are carcinogens. They cause cancer. We know benzene causes cancer and a lot of the related ones. Now, benzene, with a bunch of these connected together, let's say 3 or 4 or 6 or 10 of them connected together, those are known, I believe, as polycyclic aromatic hydrocarbons, PAH, pyrenes and terpenes, all these other things. Anybody know what those, where you might get those? Well, because of the special stability of benzene, when you burn stuff, burn whatever, if it doesn't completely efficiently burn, which it never completely efficiently burns, you're forming a lot of these kinds of things in there. So when you burn wood or plants or anything like that, and you get kind of the black stuff, that will contain a lot of these aromatic hydrocarbons, and those are carcinogens. So that's why anything involving burning things generally causes cancer. Biggest one is smoking. So cigarette smoke, those are some of the major carcinogens in cigarette smoke are these polycyclic aromatic hydrocarbons that come from burning the stuff in the cigarette, but also things like meat, or vegetables. If you grill stuff and it kind of gets that nice black, well, it actually doesn't matter if you use charcoal or not.
But just grilling it like metallizes it.
It's not even just grilling. You put a meat on a pan and it gets that delicious brownish, blackish crust to it. that's got carcinogens in it. Right. So I mean, it's good, it's delicious, but if you eat too much of it, you're exposing yourself to a lot of carcinogens, especially if it's really kind of black. And there's been some interesting studies in places around the country and around the world where it's really common to have a lot of smoked fish or smoked meat or those kinds of things tend to have a lot higher incidences of stomach cancers.
Stomach cancer?
Yeah, because you're getting all that stuff
My boyfriend's
in there.
dad smokes like every other day. He has this huge smoker machine.
Oh, like meat. Yeah, right. Like that's actually not so bad every other day. Is not a lot of cigarettes. Yeah.
Smokes every day.
Yeah. Yeah. So it's not great. Those foods are, which again, I mean, there are carcinogens everywhere, including all kinds. You can never live your life just avoiding all carcinogens. But you might think of smoked meat as something of a sometimes treat. You know. Yeah.
There's someone who smokes and they breastfeed. Is there danger that they put on themselves at the same time as breastfeeding?
Yeah. I mean, in a lot of ways, I don't know that I don't think that these particular molecules get in there because they mainly cause lung cancer, which means they're staying in the lungs. They're not getting into the bloodstream. But yeah, there's a lot of other stuff. So smoking is certainly has been shown to cause low birth weight and a lot of other stuff like that. I don't know about specifically the breastfeeding, but the molecules that cause lung cancer do so because they're stuck in the lungs there. So it's unlikely they would be in the bloodstream and be getting passed on that way. Yeah. Oh yeah, there it says in the book here, barbecued meats and automobile exhaust.
I don't love this smoke though.
Exhaust or barbecued meats?
Exhaust.
Oh.
It's like some people like to smell of gas.
Yeah. All right, so do you want to talk about functional groups or not?
Is this on
Go.
the quiz or is this on Google?
Yeah, it'll be on the quiz. Go back to the objectives on Blackboard there. I'll make sure they're updated properly, but basically what they say are, right, equations for hydrogenation or hydration of alkenes, draw the structure of benzene, define aromatic, define carcinogen, describe the difference between alkanes, alkenes, alkynes, and aromatic hydrocarbons. So you don't need to know these specific names of these things or some of the other stuff we've talked about.
Can we go back to this hexene
Mm-hmm.
added H2O to it?
Yeah. You want to try another one like that? That's a little laser. All right, so one thing I might ask is, here's a reaction. Draw the major product of this reaction. Let's see what you can draw. And again, if you don't want to think about it in terms of the line structure, then draw it out with all the carbons and hydrogens. And that can be helpful. What do you think? Something again? You wrote down something? Well, let me show you the. That is the correct structure. Now that reminds me, there's another way of thinking of this that some people find easier, especially with line structures. Instead of thinking about the hydrogen going to the C with the more H's, which is what the book talks about, you can think about the OH as going to the carbon with the more other carbons. You see what I'm saying here? You have two carbons on the double bond. The OH could go here or here. This one has more other carbons attached, so that's where the OH goes. Seems like no one believes me. Just confused. So let's look at this another way. What if I gave you a structure like this? And I asked you, what alkene did this come from? Can you draw that?
Does it mean that it comes from like numbers, square circle
Mm-hmm.
with one?
Right. So like that?
Yeah.
Yeah, that or this, they're the same. Same thing. Right. As long as the double bond's connecting to this here, the OH will go to that spot because that's where the other carbons are. Where other carbons are.
On the first example where you have the nitrogen structure,
Mhm.
why is it that the OH attaches to the original substance, not the one
Right.
that's the new one?
Here,
No, I mean the line structure. Yeah, the one down.
this one.
Yes.
Oh, sorry. I just kind of put it down there and moved the other one out of the way. It doesn't matter where you put, as long as there are two of these methyl groups, two of these CH3s, and then you the OH in the other spot. If you like that better, we can leave it like that. It doesn't matter which one goes where. All right, so what else do you want to talk about? Like the names of things? Sure. Let's give ourselves a little more space here. So you want me to give you a structure and you name it, or you want me to give you a name and you draw it? Both? Okay. Okay. Why don't you give me the name of that one?
What number do we have?
6. So this is 8, which is oct, but you have to know up to 6. And then let's draw a structure for, yeah. One ethyl, 2,4-dimethylbenzene. So draw a structure for that one. You got him? You want to give me a name? What'd you get? Well, okay. So the main part is going to be what? The main part of this is what? Octane, and more specifically, it's cyclooctane. So then we need to figure out what's before it. So what are the substituents?
4, 5, 7.
Yeah, so we've got 3 methyls, so that's going to be trimethyl. And then we got to figure out the numbers. we want to number it so that there's the lowest possible numbers. And as I figure it, the lowest possible numbers would be 1, 2, and then 4 if we go that way. Because if you start over here, you get 1, 3, 4. That's a little bit higher. Otherwise, it gets really crazy. So, so this should be 1, 2, 4 trimethylcyclooctane.
Or
Do you have to put tetra or?
If there were 4 of them instead of 3 methyls, it would be tetramethyl instead of trimethyl. Because there's 3 carbons, so I could see that. But that talks, the methyl ethyl propyl is the individual substituent, is the individual thing coming off. How many carbons does it have?
So if it was to be tried, it would be 3.
Right. It would be like a 3 carbons coming off of 1. Yep, exactly.
Right, there, it's hex octane because there's no double bond to it.
Right.
Is it
If there were double bonds, it would be octene. Right. All right, what about the structure for this one?
Is it hexene with the 3 lines?
Yep, we just drew. And where'd you put the substituents?
The top, I mean, not the top, but that one.
Okay,
I put the 2 here,
okay.
the 1 there. Put 1. I skipped the middle.
That's good. So there's the ethyl, and then methyl, and methyl.
Doesn't matter how you draw the lines.
What do you mean?
The bond.
No, as long as they're alternating. Yeah. All right, anything else you want to talk about tonight? It's your time. Whatever you want to do. Okay.
Parks question, what the Parks question? Trickiest question. Not
Like
saying,
was?
but like, I'm not saying.
Yeah, no, I know what you mean. Let's see. I mean, that's sort of what we're doing. So these tougher name type things is what would be tough on there. These kinds of reactions that we just went through. And drawing the structures. So drawing, you know, what does it mean to have something like this? Where are the carbons? Where are the hydrogens? I mean, that's pretty much it. So it's the naming, I think, is going to be the biggest thing in the reactions. What were you going to say, Alex? Yeah. Hydrogenation? So here's another thing that we didn't really talk about with hydrogenation. Another interesting fact of it. If you have a molecule like this that has multiple double or triple bonds in it, you can hydrogenate that also. Let's say we use a palladium catalyst. So the product for this, actually hydrogen goes everywhere that it can. So you would hydrogenate both double bonds in this structure. You see that? No. So what would be the product of that? Right, so the hydrogens would go here and here and here and here. Is that what you're saying? Yeah. So the product of that is just this. This is C6H10, and this is C6H12, if we count it out. Whoops, sorry, H14. So we've added, actually, in this case, 2 molecules of hydrogen. Let's do that. So let's see, we've got each carbon, remember, has to have 4 bonds. So you count the bonds shown to other carbons, and then whatever's left has to be hydrogen. So this carbon has 2 bonds to this other one, which means it needs 2 more, and those are coming from hydrogen.
So it alternates or the double bond is.
What do you mean?
No.
Like that. So those are all the hydrogens. So now each carbon has 4 bonds. So then here, if we think about the same ones, and I'll use blue for the new hydrogens. So we've added these 2 here. We still have these. And those are the 4 that we added in the reaction. You see those hydrogens coming up there? All right. What do you think? Anything else? we just stare at each other for half an hour? Or, you know, this stuff you want to talk about? You don't have to sit here if you don't want to. But I want to help you if you want to.
Are you gonna put like homogeneous and heterogeneous, like the definitions and like what to on the final?
Maybe. Yeah, that's fair game. If it's in those lists of the objectives from each chapter, that's, yeah. That said, it won't be a totally even split on the final because there will be a little bit more of this stuff than, you know, if we were perfectly even throughout the semester, just because we haven't had an exam on this stuff, this chapter. But kind of. Like I'm working on it, but it's not like the other exams that it's just I read it completely. Yeah.
It's getting super awkward.
Okay. Sorry.
Why is it comes up on Wednesday?
Why is it awkward? You're like,
What?
What are we just gonna do on Wednesday? Right?
We are gonna have a quiz, and then whatever.
I'd rather
Because everyone was like
Yeah.
doing something like,
Can we
sure,
bring questions and bring
no one's doing anything.
Sure. Yeah. Please. Please. Yeah. Please bring questions on Wednesday. I don't have specific things to say, so it's whatever you want. And yeah.
You were.
And can you please go over
There-
everything?
on
Is
the
not
copy
a
on Wednesday. Maybe take a couple of ideas for that.
How many questions do you have in mind for the final? I know it's not done.
I
but-
can't remember what it is because it's like a standardized kind of thing. I believe it's like 40 questions.
And that's what you said, it's all multiple choice, right?
Yeah. I'll have that information for sure on Wednesday. So, yep, see you Wednesday.
You probably want to lie down and catch a